Okay, I noticed that for this lesson, I really didn't do a super job on the first video, so I'm just going to give you a much more complete vision of what I was talking about. The first thing I want to talk about is just a review of what happens when you look at the equation and try to tell what the graph is doing on the ends. So on the left and the right, what is it doing? Is it going up on the left or down on the left? Same thing on the right, is it going up or down? So if you look at your function, you should be able to find something called a leading term. Now that's not necessarily the first term on the left. Sometimes it's in the middle or at the end. But your leading term is going to be the term with the highest degree. So if the x to the third, if 3 is the highest power, then that term is your leading term. So you find that term and then you look at it and say, okay, either the degree is going to be an even power or it's going to be an odd power. If it's an even power, that means that on the ends, both of the endpoints in the graph will be pointing up, or they're both going to be pointing down. So how do you know which it is? Well, if the coefficient, that's the number in front, is positive, both ends pointing up. Coefficient in the front is negative, both ends are pointing down. Now, let's say that degree is an odd number, like a 1 or a 3 or a 5 and so on. Well, that's different. With odd powered functions, you have endpoints that go in opposite directions, so they're either going like this or like that. So if the coefficient in front is positive, that means they're going like this. Lines fall into this category. Positively sloping lines go like this. They point down on the left and up on the right. And all the other odd powered functions as well. Negative coefficient in front of your odd degree term means that it's going to look like a negatively sloping line. It's going to point up on the left and down on the right. Now on the first video, I showed you how to do this and this one and this one. May look a little bit different than what I have because I explained it slightly differently. But number 3 and number 4 were very quick or not at all. Number 3 I didn't show you at all, and number 4 I just showed you really quickly. So I'm going to try to complete this lesson with this second video. Now, one of the things you might see on this notebook is I really tried to emphasize that the 0 has to be on the right. So with question number 2 and number 1, you can notice that that was the first step. That was the first thing I did, is I got all the other terms over to the left and I got the 0 on the right. The 0 must be on the right. As you can see, I've written that at the top of every page. Okay, I moved the x and the 3 over there by subtracting on both sides because I need to get that 0 on the right. Okay, so you can see that's what I did here as well. I took this equation, or inequality, and I subtracted 1 on both sides so that I had a 0 on the right. And then I said, okay, basically this function is my f of x, and this is basically a question. If I can answer this question, I can solve the problem. So what is the question that this statement is making? Basically, this is saying, where is f of x greater than or equal to 0? So basically that's saying, where is this function above or on the x-axis? So once I state that question, now all the rest of this work is trying to answer that question. The first thing I did is I wanted to make one whole fraction, because in section 2.6, we learned how to graph fractions that look like this. They're called rational expressions. So obviously we can't graph this because that doesn't fall into any kind of category. So what I wanted to do is go ahead and combine these two into one fraction. So I multiplied the minus 1 by x plus 1 over x plus 1. I changed it to plus because I distributed with the negative 1. And then once I found a common denominator, I simply added them together to make one whole fraction. Then this is a rational expression. This is what I use to make my graph, because I know how to graph rational expressions. First thing I did was found the x-intercept by making y a 0, which is x at 1, which I put a dot right there. The y-intercept is where the x is 0. So I put the 0 in for x, and I got negative 1. So 0, negative 1 was a y-intercept, so I graphed that there. Vertical asymptote, you look at the denominator of your fraction, and you know that that denominator cannot be equal to 0, so if
is there's a vertical line there that the graph cannot cross. Turns out that would be at -1. So I drew in my vertical asymptote there. Horizontal asymptotes, you compare the top and the bottom degree. If they're the same, like this one is, you take the coefficients and you divide them. So y equals 1 is our horizontal line position for our asymptote. And then finally, I just kind of tested a point just to make sure that there was indeed a curve here and another curve up here. Sometimes we get ones here and here, but the other one is not just here, but this was the other one. So I knew that there was a curve up here as well as down there because I tested the point. Some part of my graph had to be going through -2, 3, so obviously there's probably a curve right there. And then finally, going back to the original question, where is the graph above or on the x-axis? Well, this whole section up here is above the x-axis, and then this part right here is above, and then this part, that little point right there, my x-intercept, is on the x-axis. So I'm going to count that too, because they want us to tell them what is on the x-axis. This section on the left goes all the way to -infinity. On the right, it hugs right up against this x value at -1, but it doesn't actually touch it. So the right boundary is -1 with a parenthesis to say it's not included. However, here, the leftmost boundary is 1. We're going to include that because they want us to include anything on the x-axis. And then on the right, it goes all the way up to +infinity. So that is my final answer for number 3. Number 4 was a question about free-falling objects. It's more of a physics question. This is the generic physics formula that models free-falling objects. It measures the height, I should say, of free-falling objects. You might know other physics formulas that model things like velocity and speed and things like that, but this one measures height. The good thing is that this one, on this one, they give you the formula basically, and they ask you, when is the height going to be more than 64 feet? So this is your height, the height. When is it going to be more than, greater than, 64 feet? 64. When is the height going to be greater than 64? Well, the rest of the solving process is just like the others. I'm going to try to get that 0 on the right-hand side. Then this is my function. So the basic question I'm trying to answer is, where is this function, let me graph it, going to be above, greater than means above, the x-axis? So I use the left and right-hand behavior indicators that we wrote on the front page of our packet, right down here. And I determined that this would be a graph that's pointing down on both ends. Now I know that this is a parabola because if the highest degree is a 2, it's got to be a parabola. And since it's pointing down on both ends, it's got to be an upside down parabola. Then I found the x-intercepts by first factoring out a -16, and then I can just ignore the -16. That doesn't help me find any solutions. But this part I factored into t-1 and t-4, set them equal to 0, and I had two x-intercepts, one at 1 and one at 4. So where did this graph exist above the x-axis? Obviously right in the middle part here. So between 1 and 4 was my answer. So at what time interval after you shoot this rocket up into the air is it going to be higher than 64 feet? Well, any time between 1 and 4 seconds. And I said strictly between because they said above 64 feet, not at 64 feet. And that's set 2.7.